Welcome to Maths with EJD. In this video, I'll be showing you the Python code for the Erdős-Rényi model, which is a prime example of random graphs. So don't forget, I already said it, that random graphs actually have, uh, so for their degree of distribution, right? It follows a Poisson distribution, and then there's no inherent community structure or clustering. So the clustering is low, and then it is used for analyzing properties like connectivity thresholds and the emergence of giant components. So that's for random graphs, especially Erdős-Rényi model. So what this video is about is to show you what it looks like, how to implement it, how to represent the Erdős-Rényi model in Python using the NetworkX library in Python. Okay. So of course we have two major libraries here. As you see in line 1 and 2, we have the NetworkX for the graph itself, for the network, and then we have the matplotlib to show us what it looks like. And then in line 4, right? Okay, of course that tells us parameters for the random graph. So we have two parameters if you want to show the Erdős-Rényi model. So line 5 tells us the number of nodes. So you can choose the number of nodes you want. Then the probability, you can vary that. So here the probability is 0.05. And then line 9 is actually where the actual work is happening, where we are generating the Erdős-Rényi random graph. So we say random graph is NX. That's, you get the Erdős-Rényi graph as a function or module, if you like, from the network X library. So, and then the parameters are the number of nodes that you would have declared in 5 and the probability that you declared in 6. Then from 12 to 15, that's where you show the figure. So plot the figure 8 by 8, then nx.draw, then you pick the random graph, the node size is 50. You can work with all of that. You can change with labels if you want and all that. So then if you want, you can also put your title and then show. So if I run this, it just gets the graph like that. So this is what the graph looks like now. Okay. But of course, we also want to tweak it to see other possibilities, right? So for instance, you can change the number of nodes. Maybe you don't want as many as 100 nodes. Let's even start with something simple that we can handle. Say you have, let's say we have four, okay? We have four nodes. So see what that looks like. There's no connection because the connectivity is very low. Now, can we try? What if we say the probability of connectivity is actually 1? That means there's sure connection. So if the probability is 1, you can say that it gives us what we call a complete graph, which is one of the special types of graph we saw in the very first video. So you can then begin to vary the number of nodes. So the first complete graph that you can have is maybe with two nodes, right? You just have the two nodes connecting like in a straight line like this. Then if it goes to 3, for 1, you just have a single node, right? So if it goes to 3, you have like a triangle. And so a triangle is, in this case, is like a complete graph. So you can go to 4, that which we just saw. So it's a complete graph this way. Then you can go to 5. Okay. If you do 5, things are getting more complicated now. If you do 5, then if you go 6, you have something like a hexagon, and then it's complete also because for a complete graph, right? Any pair of nodes you take has an edge joining it. So that's what a complete graph looks like. So you have this one too for 7. You have for 8. You have for 8. Okay. So you can see it's getting complicated gradually, now more complicated. So if you have for 9, see what it looks like. So it's coming out that way. So you can go for, say, 10 and then see what it looks like again. Still looking nice. Let's say, okay, let me jump to 20 now. Let me jump to 20 and see what that looks like. 20. Okay, I mean, 20 is still sweet. In fact, I don't want to touch that. It's looking really beautiful. Let me move to another cell and do like, say, let me go for 30. Of course, don't forget all this is with a probability of 1, meaning that there's assurance that all edges will be joined together and you will get complete graph. So this is for 30 now. Okay, this is for 30, C20, C30, then okay. Imagine what 40 would look like. Let's say this is 40. This is 40. Okay. It's getting serious. Then let's say 50 now. Go to 50. See what you have. Okay. And then okay, I'll just stop. I'll do 100 and I'll stop there. So imagine we go here and we have 100. Okay. So this now, yeah. So it's really dense like that. And of course, we can now begin to, okay, let me copy this out and say, and so with these 100 notes, can we now begin to relax the probabilities? Instead of instead of 1, can we do 0.9? What does that look like? So it means that so it's not that guaranteed anymore that all the edges will be joined like that. So you can see that there's a bit of, so if you look around here, there's a bit of, so you have some that are not connected per se, unlike what you have here where everywhere is connected. So what if we reduce it to say 0.5, you know, so see 0.5. Okay, so you still have, so things are loosening up gradually. So imagine 0.1 to 0.1. Okay, so it's getting sparser and sparser. Um, Now I'll also like to see if we have fewer notes. Okay, I think did we try anything with fewer notes? Okay, let's do fewer notes so we can actually grasp. Okay, I think I started from maybe just 3 notes. So with this now, with 0.1, can we try like 10, just even 10 notes and see what that looks like? Okay, I mean, you see not all the nodes are joined together. And then the graph formed is not a connected graph, meaning that you cannot reach any node of your choice, either directly or indirectly. You can only reach some. Okay. So what if I make this like 40 now and with that probability of 0.1? Okay, so we can have something like this. So I mean you can play around with this whole thing. So it's just you have just about 15 lines of code. Effectively, if you remove all the comments and all the spaces, maybe it's just 1, 2, 3, 4, 5, 6. So it's just like 9 or 10 lines of code to get this going. Okay. All right, so watch out for the next video, which is gonna be on the Strogat's model, which is a very good example of small world networks. Okay. Of course, you want to subscribe to this channel so you can keep abreast of whatever is happening here. By also hitting the notification bell. Comment, let me know if you want to teach a topic or solve a problem. Like and share so that more people can have access to this great content. Till I come your way again, keep networking. Bye.